Hi again, everybody, and welcome back. We've just gotten done talking about conservation of energy, all right, and the idea that all the mechanical energy initial for an object in its initial position has to be equal to all the mechanical energy final in its final position. And each of these energy states is a combination of two kinds of energy: kinetic initial plus potential initial, and then kinetic final plus potential final. So those two energy states are sums of those two types of mechanical energy: kinetic and potential, kinetic and potential. Let's see if we can solve this problem right here using that very principle. Okay, so we've got somebody at their graduation ceremony, and if you have never been to a graduation, you may or may not know that there's a time where everybody throws their caps up in the air. So this person is throwing his cap up in the air, and it's leaving his hand at 7.85 meters per second. We have a mass of that as well. By the way, I should probably be writing down these knowns. Mass equals 0.120 kilograms, and velocity 1 equals 7.85 meters per second. All right. We can also ignore frictional forces. In the real world, the friction between the air and the cap would slow it down, but we're going to assume that there's no friction, and we're just using conservation of energy to find what? To find the speed of the cap when it is a certain point above the release point. All right? So V final, that's our big question right there. Okay? I forgot to write down that what is this 1.18 right here? That is our height, right? The height that it goes up, 1.18 meters, and that's going to be helpful because we have an energy state here, energy initial, and energy final. And one of those types of energies is potential energy, and potential energy is a result of the height. So, energy initial, we're assuming, is going to be equal to energy final because we're assuming there's no loss of energy. There's no energy has been wasted. Okay? So we can say kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. As one goes up, the other goes down over the course of that change, and vice versa. But we want to find the final speed of the cap right there. So which one of these values is going to have final speed in it? Well, it's obviously not these because these are initial values. Final speed is going to be in our kinetic final right there. So we're going to solve for that final speed where it's inside that kinetic final right there. But it means that we need to kind of write out our values in a little more detail. All right, kinetic energy initial. That's 1/2 kx squared. I'm thinking of k. 1/2 mv initial squared. That's our initial kinetic energy. All right, what's our potential energy initial? Well, the nice thing about potential energy is that you can call 0 wherever you want. So in our diagram right here, we have this position where it's marked, where his hand is right here. This is marked as 0, mgh. Since we're saying that h equals 0, then that whole thing is going to be 0. So we're going to sort of assume that this is 0 potential energy, and it only increases in potential energy as it goes up. Okay? Equals what? So this is really going to be 0 right here. So that's the nice thing about potential energy, the fact that that'll become 0. Our final kinetic energy. Well, that's going to be 1/2 mv final squared, which, by the way, we're solving for that, plus our potential energy final. That's mg. I should really call this h initial right there because this is going to be h final. Our final height is 1.18 meters above the launch point. And if we call the launch point 0, then it has gone up 1.18 meters. Okay, so we have all of our energies described in more detail. Kinetic initial, potential initial. Kinetic final, potential final. All right, well, let's solve for this V final right here, because everything else we know. Everything else we know. First of all, I'm going to subtract over our MGH final right here. And I'm going to make this 0. So this is going to go away, and this is going to be subtracted over. All right? So 1/2 mv initial squared minus mgh, or our h final, that's 1.18 meters, equals 1/2 mv final squared. That's a squared right there. It looks like a 7. Final. Okay. Well, look at this for a second. What do you see that we could get rid of? Now, we're ultimately solving for our V final right here. But all these values have m in them, right? And we're told the mass of the cap, but it turns out we're not even going to need it because the mass of the cap is going to cancel out. We can get it out of our problem entirely. All right, so that, and that are all going to cancel out. Okay, well, we've got everything equal to 1/2 v squared. Let's get rid of this 1/2. First of all, this 1/2 and this 1/2 cancel out, but it doesn't cancel out right here. What do we do to get rid of this 1/2? We multiply by 2. And of course it cancels out this right here, but that means we're going to have to put a 2 in front of this GH. So if we cancel out the 1/2 and we account for the 2 in this one right here, it's going to be V, oh, I meant to be writing in red. V initial squared, and I'm also sort of writing on the crowd behind us right there, minus 2GH equals V final squared. All right. V initial squared minus 2GH equals V final squared. Again, this 2GH comes from the fact that since we multiplied this by 2 to cancel out the half, and this by 2 to cancel out the half, we had to multiply this by 2 as well, so that's where the 2 comes from. So finally, we're going to say our V final is going to be the square root of V initial squared minus 2GH. All right, I'm kind of running out of room right here, but I think I can fit it all in. Our initial velocity squared, that is 7.85 squared minus 2 times 9.81. I thought I could fit it all in, times, what's our height? 1.18 meters. 1.18 meters. In fact, you know what? I'm going to clean that up a little bit. I'm going to just take all this stuff and shrink it down so I have a little teeny bit more space. There we go. And I'll write it all in the same line. Again, times the square root of 1.18 meters. Should have thought of that before. So our V final is going to be what? I get a value of 6.2 meters per second. And that should make sense because remember we said that as potential energy increases, kinetic energy decreases, and the opposite. As kinetic energy increases, potential energy decreases. Well, as this graduation cap is going up, it's increasing in potential energy, which means it's decreasing in kinetic energy. That's indicated by the fact that it has a slower velocity, a slower final velocity than it did originally right here. So some of that kinetic energy was turned into potential energy that it has more of at this higher height. All right, so that's a good first example of the conservation of energy. The idea that the total mechanical energy initial kinetic plus initial potential, is going to be equal to the final kinetic plus the final potential. Everything's accounted for if we're dealing with conservative work and conservative forces, and that enables us to find our final velocity right there. So, thanks for following along on this. If you have any questions, come see me. But in the meantime, thanks for following along. I'll see you on the next one.